So I'm going to talk today about Spark. Headline, analyzing 150 gigabytes of data for $5 in an hour. Pretty exciting stuff. So the first thing I want to do is give a shout out to my company, Perscio. They paid me to learn about this stuff, so I want to just thank them for that. We're a big data consultancy. We try to help businesses bring up their data literacy or bring big data solutions to better the business. So the second thing I want to do is get to know each other. So he described a little bit about myself. I just graduated recently from school. I was in school for mathematics. I've programmed my whole life since I was pretty young. I'm still pretty young. I'm 22. And yep, definitely like to play music. So that's, I guess I forgot to do the slide for that one. Let's talk about you though. AWS, how many people know what that is? How many people use it all the time? How many people recognize EBS? Great, that's good news. How about Python? How many people use Python? Okay. Hadoop? Okay. How many people use Hadoop in production right now? Wow. All right. You're cutting out big chunks of my presentation with every one of these. Spark. So you guys have used Spark. How many people don't know why Spark is cool? That's good. Okay, so that's what my presentation is about. That's the goal of what I'm talking about. So you've just confirmed that I don't have to just like walk off stage right now and just like enjoy the sun. All right, I guess let's continue. I want to talk immediately about the data because I'm going to confess to you that I've tempted the demo gods too much by saying I'm going to bring up a cluster and compute data on 150 gigabytes right in front of your very eyes. I will do it, but it's going to be way slower than I would have liked, and it's not going to be nearly as cool. In fact, the data that I'm using is really cool data. You could do some really amazing stuff with this data. I'm not going to do really amazing stuff with this data, but I will convince you that Spark's cool and that you should go try it out. So let's talk right now about the data. I'm doing Wikipedia page view stats. This is all available online all the way up to now. I'm using all the way back at 2011 because that was what was available on AWS. You can just get it as an EBS external block and connect it to your instance real quick. The data is formatted like this. Every file of the data is a single hour of Wikipedia time. I guess that's the same as regular time. And every row is for a single article. And they'll tell you how many times that article was viewed in that hour. So space delimited, first column is the project. You got English, French, and then there's also wiki books and a lot of other stuff. I'm just filtering out everything except for English. So I don't speak French, so that was an easy decision. The next is a string, which is the article name. In my data analysis, since I'm using a huge amount of data, I said 150 gigabytes of data for this 3 months. Turns out that those were all gzipped files. So I gun-zipped them, and it was 500 gigabytes, right? So I was like, I'm not doing that. So I'm doing a month of that, and I'm also going to work really hard to compress this data as much as I can so I can bring most of it into memory to use it how Spark should. What I'm going to do with these page names is I'm computing a hash from them. So I still get unique numbers, but they're going to be much smaller, and I'll have to go look them up later. The third column right here and here is the number of views in that hour, and the fourth column is the size of the content that was returned. So I'm just trashing that. I don't care. So that's great. I'm going to start the demo right now because it's going to take way longer than I thought. Let's get out of this. So one really awesome thing about Spark, which this is going to be fun. Okay. All right. One really cool thing about Spark is this function right here. Who has used Spark-EC2? Nobody. Great. This is an amazing thing. So when you download the Spark binary and extract it, inside the EC2s folder, there's this awesome function where you give it your EC2 credentials, your AWS credentials, tell it what region you want your stuff in, what zone, what the key is, like SSH key, so you have to generate one of those. You also tell it how many nodes you want, what kind of node, how big the drive you want attached to it to be, and it will spin all of these up, wait for them to come up, install Spark on each one of them, connect them together, and then you run this command, log in to big boy 2, and you're sitting at the master node. Amazing. I mean, it's just so easy. Makes it so simple. You download the binary, run this, and you're in Spark in no time at all. Yes. Okay, so I have a screen going where I've already loaded all of my data. I've already munged it. It took an hour and a half to take that 150 gigabytes of data, compress it, put it into memory, into this. This is the size of the final array. And you can't read that number. It's 2 billion records, a little over 2 billion records. So it's pretty big, and it's all in memory, or most of it's in memory, and that's why it's going to be slow. So we're going to immediately just assume you know what I'm doing. We're going to start this processing, and I'll explain it after the fact. Copy, paste. Okay, so it's going to start doing stuff. Let's make sure it actually, yep, it's doing stuff. Okay, let's go back to the presentation. So while it's doing stuff, I'll explain, well, most of you know Hadoop, so I'm just going to give a real quick overview of Hadoop for anybody that may have lied, or if there's people I didn't see their hands. Hadoop, the big part of Hadoop I'm using right now is HDFS. That's the file system that I'm bringing this stuff into memory from. And really that came out of, you have a huge file, 10 terabyte file, and you want to do something with it. So you can't fit 10 terabytes, or maybe you couldn't a few years ago on a single drive. So you split it onto multiple different nodes. You put a chunk on each node. And then Hadoop does some nice things by replicating things and keeping track of the different copies of it and making sure that you don't lose data. So on the base of my architecture, I'm going to have HDFS holding the 500 gigabytes of data. And then I'm going to talk about MapReduce, because that's kind of the motivation for Spark, is in MapReduce. MapReduce, you have the same file. So this is the file we just put into HDFS. And you want to calculate a computation on it. So the way you do it in this paradigm is you send to each node an instruction for what it should do with its chunk, right? So you say each of you do this. Usually you'll specify what you do with each line in the file. And it computes a new chunk out of that. This as a whole is a new file in HDFS, which is Hadoop Distributed File System, for anybody that didn't know. And then in the reduce paradigm, you'll take each of these chunks and send them to some reducers that'll then summarize those into some results. So classic example is a word count. So here's my file, except imagine it's like really long. It's like 4 terabytes long and 10 terabytes long. The map, what you send to each node to do is you just say, for each word, just return a tuple, that word and the number 1. This is an interesting example because at first you're like, why 1? What are you doing? But then in the reduce step, you can just say, go through and find all of the Alex and add their numbers together. So you put 1 here because then you can talk about like iteratively computing this, so that each node, before they even send the data to the reducer, they can do their own little reduce step. Essentially, I mean, if you don't understand some of the details of this, I'm not sure, I can't read the faces in the crowd, but if you don't understand some of this, just understand that this is a method for computing distributed data sets. Understand that you send a little instruction to each node to do something with their chunk of the data. The natural kind of extension of this, because I guess the motivation was that writing MapReduce scripts was hard. You had to have very specialized training. You had to understand the MapReduce paradigm really well to write good MapReduce scripts that would run efficiently. So I guess Yahoo and Facebook developed Pig and Hive, which used the idea of chaining MapReduces together, little bitty simple MapReduces together, to do something complex. So Hive emulates SQL, so it'll take a SQL query and then turn it into a chain of MapReduces and make sure it all completes correctly. Pig, they have their own language called Pig Latin. But I guess I'll go back here. The motivation for Spark, in my eyes, right? The motivation as to why I initially found that it was awesome was because So input, right? We pull a huge data, like a huge file into memory and do something with it, right? We pull it from disk, we read it, do something in memory, and then maybe persist it back to disk as the output. And then you'll use that as input again. So you bring it back into memory, do something with it, and then persist it back into output. And 9 times out of 10, you'll see that most of your script is just doing the read and the write of that, because disk read and write is so costly. So that's kind of the motivation of Spark, in that, Spark. So this is like 2012, when the papers were released. So the motivation of this is that now you kind of do the same thing, except you do it in memory. So instead of having these distributed files that are stored on the hard drives of this cluster that you send computations to, you have memory objects, which are distributed across your cluster's memory. And you do the same sort of management processes. Spark does a little bit different stuff in terms of how it, so I said that Hadoop does replication to make sure that you don't lose data. Spark does it differently in that they instead keep track of how you got your data. So they will keep track of the fact that you pulled it from this file, you did this operation on it, you combined it with this other thing, and now you have this new thing. So if you lose some of the pieces of the data, it'll just go back and recompute them instead of using replication. I think that's really cool. And that's my slow, here, let's check on this. Still going, what are we at? So we want that number to get to 2,300. We'll get there. I lost my train of thought, but here's some pictures from the Spark white paper. And if you really want to understand Spark and you want to know more about Spark, the Spark white paper says it really nicely. It's in layman's terms, it's not technical. It's something that most people that do programming can read. If you just search Google for Spark white paper, you'll find it. Basically everything that AmpLab comes out with, I like a lot. But you can see some of the operations that I'm using in my current case here. Map and filter. You guys are all Python people, so you probably know, I mean, how many people use map and filter? Yeah, so basically you just give it a function. So filter, you give it a function that returns a Boolean for every element, and that determines whether that's going to stay in the array. Map takes an element and passes it through a function in the same way, but it takes the output, and that's what goes in the new array. There's a union function which takes 2 of these distributed data sets and combines them together into one bigger one. And really, actually, in my analyses that you'll see, these are all we do. And then, like I said, Spark will keep track of the whole lineage of things. So this is a more complicated example where there's multiple steps. So for example, it's called a resilient distributed data set. That's the fundamental object that Spark deals in, these mystical distributed memory objects that I was discussing. So for example, in this resilient distributed data set, or RDD, if one of these nodes, the node that was carrying this block, dies, then the RDD itself, the data type, has stored in it that block was computed from this RDD by some certain operation, and it'll be able to recompute that. So this actually gets really complicated. I pulled this diagram just to show some more complex operations. This is a visualization of one of Spark's mlib functions. So Spark, it does really well on machine learning exercises just because in their nature you do iterative computation where you'll take a result and then use that against the same data set. So for example, in a logistic regression, you'll make a guess as to what you think fits the data. You'll compute the error, or you'll compute the next step, like where you think you should go from there. And then you'll take that new value and compute the error again against the same data set. Spark does that really fast because it can keep that data set in memory and iteratively compute on that. Also, I didn't mention at the beginning, feel free to ask questions. Does anybody have any questions right now? No. Good.
So is there a relationship between Hadoop and Spark, or are they just totally separate? Like, does Spark rely on Hadoop? Or?
Spark doesn't rely on Hadoop. You can run Spark by itself. Like I said, I used HDFS on the base because if you are, say you're loading a giant text file, like I'm loading 500 gigabytes or 150 gigabytes out of the disk, then because you have that already in a distributed fashion in HDFS, when you bring that into memory, it can do it in parallel. So it speeds things up. Yes?
So you mentioned logistic regression as an example. Overall, how is the algorithm support with Spark right now via Python?
I hear it's pretty good. I'm not really in depth in machine learning algorithms. So I know that they have focused in the last 3 years really hard on the mlib, which is, I mean, you go to the Spark page and it's like there's Spark streaming, which is also really cool, and then there's mlib. And there's also a graph computation thing. But I believe that they work really hard on that. So they like to compare machine learning algorithms. That's what they do their benchmarks on, because there's no way you would write, for example, the logistic regression example that I just did, there's no way you would write that in Hadoop just because of the nature of it. So they show benchmarks like 100 times faster than Hadoop, and they'll show like a crazy graph just because they chose that specific thing. But anyways, so here's a more complicated example. You can see, whoa. You can see that there's a, they call it a DAG, directed acyclic graph of computations, where each RDD basically knows where it came from. So when an RDD fails, it can ask, how do I recompute myself? Another note, RDDs as a data type exist on the master node. So in the setup of Spark, you have a master node and then you have a ton of slaves. And the master node basically just coordinates all this stuff. Coordinates the RDDs, figures out what's where, submits jobs, all this stuff. Speaking of, nope, still going. Yeah, it's just a native data type, an abstraction that exists on the master node. Just as a note. Does anybody have any other questions before I continue? Yes?
Did you do your analysis using the PySpark interface, or did you do it straight in Scala?
Nope, I use PySpark.
Okay.
I kind of had to, but I use PySpark anyways because I'm very familiar with Python. I also want to note that I recommend, if you do this, that doing it like this, where you paste code into the interpreter, is super useful. Just because you can load all your stuff into memory, munge it, and then once you have like your key data set, the thing that you're going to use for your analysis, then you can just iteratively compute on that without having to bring it back in and out of memory, without having to do these expensive disk writes and reads. And I guess I'll try to explain that better in this next slide. I'll give you kind of an example of me running a Spark script. So I'm sitting at the Spark terminal, PySpark, and I start running commands. Here, I'm bringing a file out of S3. So also Spark works really well with S3. It can parallel load really fast from S3. So here you see the Spark context. That's just a kind of a wrapper for all of the stuff that denotes where your master node is, where your Spark cluster is. And this text file thing, you can use that for HDFS, you can use it for S3, you can use it for just a text file. And over here on the right, you see the execution time. So for this, execution was instant, which is something that you might not expect because I'm bringing a text file, maybe a huge text file in from S3. The reason for that is because Spark is extremely lazy in that it won't compute something until you have to see it. Until you say, what was that thing that I asked you for a while ago, and then it'll be like, okay, I'll start computing stuff. But it's nice, actually, because it has this whole directed acyclic graph of computations, and it won't compute something until it actually knows that you need it. So once you ask for something, so let's say I say this, and then I say, just take one line of that file. It'll be like pretty fast, even though this is maybe a 100 terabyte file or something huge. And the reason for that is because it's like, oh, all I need is this single chunk of this HDFS file. So it does some nice things, and it'll also do optimizations in the background. So let's keep going. So these are tweets. Each line is a giant JSON object that represents a tweet. How many people have worked with Twitter data? Okay, good. This isn't going to be Twitter data heavy. import JSON, parse the JSON tweet, right? And then I actually, this file had, every other line was blank, right? So I ran, this tweets variable is actually an RDD already. I loaded the text file and it's like, okay, that's an RDD, that's a resilient distributed data set. So this filter command is a command I'm running on an RDD. So I filter out all the blank lines and then run a map onto JSON. So it'll ship that to each node of the cluster and tell it to run that on its chunk. Again, instant because I didn't ask for anything. Here, I'm extracting the text. And I'm also running this, cache, which is one of the most important things in Spark. It allows you to tell Spark what you think is important, what you think it should keep in memory. And then, so for example, I know that I'm just going to do iterative computation on the text of these tweets. So I want you to cache that in memory and keep it around. So this is where the real magic comes in. I say filter those tweets that have the word Hannah in it, and I count those. So I'm actually asking for something to come out. And it gives me a number after 20 minutes on a 3-node cluster, 50 seconds on a 15-node cluster. So it actually did some computation. It was like, right? Then I asked the same thing again, except for a different name, Alec. It gave me 12, but it was less than a second, right? So this kind of illustrates why Spark is cool. And that's that this 20 minutes, this 50 seconds, most of that was bringing the data in and doing these steps. And because I know that this is the important thing, and by this I mean this is the important thing, right? This is the thing I care about. Here, it just goes straight back to the cached memory object, and it's practically instant. I can talk right now, actually, about why this is taking so long. What are we on? 2275 out of 2362. The reason this is taking so long, and maybe if we scroll up, I can see. So you see this is like 60,000 milliseconds it's taking to complete each task. That's not good. And I can't go up far enough. I should have shown you at the beginning. But actually the first 90% of these jobs finish in 50 milliseconds. And the reason is because I've already loaded all that stuff into memory. I've already figured that stuff out, and I cached it. The reason these are taking so long is because I didn't give my cluster enough memory. And that was kind of the error I ran into today. And because it takes an hour and a half to load this stuff into memory, I didn't have the opportunity to just add more nodes and recompute. So that's why this is taking so long, because it's actually going back to the files, and it has to re-grab that stuff and munge it or whatever, bring it into memory. We can talk about the actual computation that I did before you came here. Maybe. So this is stuff you didn't get to experience. Here I'm using hashlib. That's the library that I used to create the hash that I was talking about earlier. I'm running on a 17-node cluster, and this HDFS file contains the names of all the files in HDFS that I'm loading from. So I have an array of files that I want to grab, totaling approximately 170 gigabytes of stuff. This is the magic function, which basically compresses. Can you guys read this, by the way? I can't tell. Raise your hand if you're having trouble reading this. Really? Okay. So this is the magic function that I was talking about that compresses the file. Basically, all it does is computes a hash of the name of the article and returns a parsed number of views. I know I said magic. I may have oversold that. Here's where we actually start doing stuff. So here's an empty array that I'm going to fill with RDDs, one for each file. And the reason I created one for each file, I guess I'll explain after a few lines of code. Here I actually parsed the name of the file to figure out how many hours that is from hour 0 of 2011. Right, so I convert that into a nice format because the file names were kind of, I mean, it was like 2011 dash whatever. It was some date format. I turned that into a number for the total number of hours since the beginning of the year. And then here's where I start bringing my text files in. So it natively supports HDFS and does some nice things to parallel load these into memory. Here, let's keep looking. So here's, I said this, right? I was going to get rid of everything that wasn't English. I map it through that function I just showed you that does the nice, cool compression stuff. Then here, I had to look this up because I couldn't figure out how to do it. But you know, I have this total hours thing. I'd like to put that into the row, into this. I'll show you. So what comes out of parse raw, this function, is a little array of just the number of views and the hash. I'd like to put the total hours into that as well. So I don't know if any of you guys have seen passing a function, like a variable into a lambda function, but it confused me for a little bit. Anyways, that's what that does. So now I have a giant array of size 3 arrays, which have the hour since the beginning of 2011, the number of views, and the article. And then I put all these RDDs in the array and union them together. So now I've got one gigantic RDD, one giant array, and I cache it. So this is what I did. After this, actually, I should just put it in here. I run another command, and that's working.count. So I just tell it to count the number of things in there, and that's because it didn't do anything up to here. It was like, it took like, it was momentary for me to just paste all of this stuff in. It was just instant because I didn't ask it to give me any results. So I called working.count, and then I just did a very simple analysis just now. Which is,
You might need to escape out of your scroll.
oh, you're right. This might be done. Yeah, okay. Well, and I had, okay, so I'm just going to say, I also hadn't used Screen before yesterday, which Screen is just amazing. It is just an amazing thing. What was that? Okay. Here, I'll just write that down right now. But anyways, I couldn't figure out how to put this into history. I looked it up. It was fine, and I put this exact thing into an Excel document. So I'm just going to show you the results that would happen if I just copied all these numbers and put them into Excel. And they look like this. So this is the total page counts. And I did preface this with, I could do so much cooler stuff with this data, right? This is just like, this is like a first thing you do with this data. But here it is, you see a nice cyclic thing. You can see the weeks bouncing around. You can see the days. Yeah, I see a little dip, like somewhere around, I don't know, honestly. I don't know what time that is. But since it's English, it's probably afternoon. So that's essentially my result from that. Does anybody have any other questions? I'm going to ask right now. Uh-huh.
So do you run into MapReduce? What happens if the data is more than your memory size or your hard-disk instance?
Yeah, you don't want your working data to be larger than your memory size because you're going to run into what I just ran into, where it's not quick. It's not what Spark should be. It's not what you want. That thing did finish, but I would have preferred, if I just doubled the memory of my cluster, I could have shown you a half dozen computations just now instead of just one. So it's, I would prefer that the working memory, at least the object that you're going to be working with, should fit into memory. Yeah. Yes.
I'm looking at how do you handle data quality in the sense that within the context of what you want, if you want to use this for more word like the name of a person or something else that is not exactly context. That could be counted twice, whereas they are two different things. So different data quality things, how do you do some quality stuff?
Yeah, I mean, it's just like usual. I mean, the biggest recommendation I would have towards, I don't know, trying to do something big in Spark is to not start big, right? You don't start on a 17-node cluster. You start on one. You start on standalone, and you make sure your functions work. You make sure you can do it on one file. I mean, it's a pretty classic thing, but I ran into it. I was like, okay, let's just start up the big cluster. Let's do it. And it just didn't work. As far as data quality, I mean, it's a general purpose data processing language. So anything that you would, any solution that you would have would translate. I mean, I don't know, am I answering your question? Yeah. I forgot I had this slide, so I'm going to talk a little bit about like what was going on, how I set this up. I set up a 17-node cluster, so each of these are nodes. Each node had a 50 gigabyte external hard drive, EBS, totaling 850 gigabytes, which I figured was plenty for my 500 gigabyte data set. And then I connected that wiki EBS volume to the master node. And once Hadoop was up and running, I just wrote a bash script to copy each one of those into HDFS. That took probably 6 or 7 hours. So if you're looking at making money, also this 17-node cluster I spun up, I said it would cost $5 for an hour, but it actually costs like $1.30 because I used different instances. So this is something that's extremely affordable. You can go home, download Spark, and run the EC2 command that I was talking about and start doing this yourself in no time. Anyways, ran HDFS over the EBS volumes, which actually took me longer than I was expecting, but and then Spark on top. Yes?
I got two questions. First, are there any heuristics or any guidelines to know how much memory you're going to need based on your computations?
Yeah, I mean, so I had 500 gigabytes, right? I probably narrowed that down to 170 because I don't know if I told you or not, but I only did 1 month because I was like, that's a lot of data. And I promised 170, so I figured I'd deliver on that. You have a general idea of the compression ratio. So we were talking about how much I could compress into my working set. So I was like, I can make a long, that's a hash of the name. I can turn that into an int. I'll throw that away. These sort of judgment calls give you at least an idea of how much you can compress this. Also, Spark needs about half of the memory of the node just as buffer for itself. You can tune that, but I don't know enough about what it's doing behind the scenes to want to tune that. But yeah, there's definitely heuristics where you can just do some back of the envelope calculations and figure out what you need to do. And a lot of times that'll guide you in the right direction where you're like, oh crap, I'm not gonna be able to do this. Yeah.
Is there a way to actually parallelize the sharding, or does it have to go to the master node?
This?
Yeah, but when you're basically loading, you have it kind of going through the master node. You actually parallelize that so that you can shard multiple.
Yeah, you certainly could. So I could connect this EBS block, like volume, to each of these guys, and then be running the same commands on some subset of those files, and it would have happened way faster. But
is it just more money? That's why you didn't do it?
it was more time, actually. That was why I didn't do it. It actually costs more to do it this way because I had a 17-node cluster up for 6 hours while I was loading in that data. But I didn't have the time to figure that out and do more about that. So it's definitely possible. Yeah. But is anybody not convinced that Spark is cool? Are there any other questions? Because I'm out of content. Yes?
Real quick, you were mentioning that you couldn't add nodes. Can you add nodes on the fly or?
Kind of. In the EC2 thing, you can just go into your EC2, look at your instances, and if you create a new node inside the EC2 slaves, you can go back to that EC2 script, shut down the nodes, and bring them back up, and it'll actually do all the install stuff that it did on the new node and make sure it's in the group. So pretty nice. That's what I would have done if I, didn't have that
But
overhead.
you lose the in-memory stuff that you already performed.
Yes.
Okay. So you can't just add a node and expect it to work on the other nodes that already are up.
No, and you could add a node and then put it in the configuration files and then start a job, but now that I was already in a job, there was no way to do it. No hot swap. I don't think. I mean, I'm guessing the creator of this could probably do it. He'd probably know how to do it, but I don't know how to do it.
I think that's the notion of the Spark context. You're initializing that context.
Yes. Yes, and there's probably ways to like tell it about a new block manager or something, but I don't know. And yeah, I didn't have the ability to do it. But yes.
Well, I like what you presented because it depends on your cost to benefit factor.
Mm-hmm.
So to me, I feel that even if you could have several multiples of 500 petabytes of data that you can then parallelize, and each one of them might have to go through this depending on what kind of money you're willing to spend. But to me, I'm thinking that maybe it can be a combination of more than one technique towards achieving better performances. But this is actually one way to get it done as well.
Yeah, and a lot of the stuff behind doing this, so when you sit down and you're like, I'm going to analyze 500 gigabytes of data, a lot of it is back of the envelope calculations. I actually made the mistake in this specific instance of making too many assumptions and making too many calculations and making too many of those things. And then I ran into issues that just broke my assumptions, and everything that I had like gone from there went away. So I definitely recommend that instead of like doing, unless you have like large experience in this stuff, instead of like making all these assumptions and then spinning up the 17 node cluster and then just like running your script at it, you start on one. You can do that for 17 hours in the single hour that you spun up the 17 node cluster. So just a cost benefit kind of thing.
Excellent. Any more questions?
I just actually have one more. I noticed that your scale was not linear. Like when you had 3 nodes and you went up to 15, it actually dropped by like a factor of like 30 or something, or 60 versus, it was some, right there, back up to the 20. So it was like 20 minutes for 3 nodes. You'd expect if it was linear, you'd have a 5 times performance, so you'd think it would take 4 minutes, not 50 seconds.
Mm-hmm.
So why is there a greater than linear increase when you go from 3 to 15 nodes?
I don't know. Sometimes these things are more complex. So like, I mean, in the 15 node one, there were a lot more jobs. So it might be just in that managing those jobs was some of the overhead. I'm honestly not sure. I didn't investigate into that.
The reason why I asked that is because you said if you do 1 node, it takes 17 hours, 17 nodes takes an hour, but it almost seems like it would take less than an hour because it seems like it's greater than linear performance.
Well, and yeah, sometimes there's these, I guess, critical spots. So like if I had 1 or 3 more nodes, I could do instant calculations on my data because the only thing that's holding that up is about 600 of the splits, which I have to bring from disk, and those overwhelmingly trump all of the rest of the compute time.
Okay.
So sometimes, sometimes it's nonlinear for sure.